Very often we want to deduce what the term structure of interest rates are. One of the bigger discussions in fixed income is estimating the yield curve. Yield curve is not that straightforward to obtain. It's unlike yield to maturity, or it's not exactly consistent with the idea of estimating the internal rate of return or a flat rate of return consistent with the bond price. When we're estimating the yield curve, we're trying to determine the interest rate over a given period of time. So there is a yield, and then we're looking at the behavior of interest rates, and we're taking as a benchmark some bond issuance, generally sovereign government bonds, because markets are so liquid and one bond is relatively equivalent to the next bond in terms of credit risk. And so, and typically also with government bonds, we don't observe differences as a result of hugely different specification or covenants in the bonds. Bonds can be relatively uniform, but even more importantly, same level of credit risk. Also with term structure, because of investor preference, because of the unwillingness of investors to be locked into bonds for longer periods of time, we very often find that for shorter dated instruments, the yield on the instrument is frequently less than the longer term instruments. So to hold on to an instrument for a short period of time, in some respects, if you buy a 1-year bond or a 2-year bond, you're more senior than somebody who's locked into a bond for 10 years or 25 years or 30 years, because there's a lot of inflation risk and other macroeconomic variables that could be not always known in advance, and you need to be compensated for that. So term structure is quite subtle, but it's also important as a benchmark for different types of discounting. There are different shapes. Bond curves don't always have to be sloped upwards. Bond can slope downwards. Again, if there's some imminent sense that inflation is going to fall, interest rates are going to be cut, or if the immediate term to medium term outlook for economic performance and GDP growth is slightly negative, investors may expect to find interest rates being cut. So yield curve is something that we estimate. It's something also that is a predictor of future macroeconomic potential, or what investors or bondholders typically expect to happen in the economy, because interest rates are intimately linked, and monetary policy is intimately linked to what's happening, the fluctuations in the macroeconomy. Okay, so we're interested in term structure. Going to take a simple example here. What if we have 4 bond instruments, 2 of which pay coupons, 2 shorter dated instruments, 6 months, 1-year instruments that pay no coupon? And how do we deduce what the interest rate is consistent for the time period? So we have 6-month, 1 year, 1.5 years, 2-year bond instruments. So I've just got onto this web portal here, investing.com, and I'm looking at find government bonds. So really we're looking at this America, and then we'll pick out a country. So we're looking at the Americas and look at United States, and then we'll search, and we're looking at maturities, and we're looking at the term structure of interest rates here. So the yield curve 3 years ago, 2 years ago, and where are we? Current, is it current? And then the rate of interest for 1 month, 3 months, 6 months, going up to 30 years. Longest dated instruments for US Treasuries is 30 years. Let's look at Europe for a second. and then look at Germany, which is probably a key benchmark sovereign debt market. And when we look at interest rates in Germany, well, we've something unusual here. We have a negative range, and that means that if you're a pension fund, you're willing to take a small loss on holding the bond. You pay the German government for giving them your money, which is very unusual. But for 6 months, 1 year, 5 years, what's the current one? This is the current one. Interest rates are this bluer one. The current one is the bluer one. So interest rates have gone up a little bit. Compared to 3 years, compared to 1 year ago and 1 month ago, and then the current interest rates, there has been a kind of parallel upward shift, or somewhat parallel upward shift. But again, what we are fundamentally looking at is different maturities, 1 month, 3 months, 6 months, in this instance all the way up to 30 years, and then the yield in the bond. And because it's term structure or yield curve, we have to strip out the effects of the coupon. So basically, when we say 30-year yield from the term structure, we mean you invest an amount of money today, in 30 years time you'll get an amount of money back. It should normally be higher if interest rates are positive, and the rate of return is 1.3%. So the rate of return over that period would be 1.3%, which is historically quite low, almost artificially low. Okay, so to see that then perhaps in an estimation, how we might actually implement a term structure type estimation. Again, we take a very simple set of data, how much you currently would pay, the current bond prices, the coupon structure, none in some instances, and some semi-annual coupon here, 4 and 5 at the 6 monthly interval, and then the maturity of the bond. So this one is for 6 months, and then after 1 year you get, after 6 months you get 100 back. You put in 89 today, after 1 year get 100 back. Put in 94.84, get coupons at 6 month intervals, matures in 18 months, get 100 back face at the end, and then the 2 year bond, you put in 97, pay 97.12 today, that's the market price, get 5 coupon, 5 every 6 months, $5 coupon, it matures in 2 years, at the end of the 2 years you get this face value of 100 back. Okay, so the first two, actually to deduce what the interest rate is in those two, relatively straightforward. We just set up an exponential, so if we're trying to work out the continuous interest rate, we consider this exponential term e to the power of 0.5 by r. We don't know what r is, we've got to solve for that, but we know if we invest 94 today, at the end of 6 months we get $100 back. What's the implied rate of interest that's continuously compounded? We do some manipulation, we bring the 94 over, divide both sides by 94. Then to eliminate the e, which is a problem here, we take the natural logarithm both sides. Natural logarithm of e0.5r is just 0.5r. So by taking natural logarithm here and on the other side, we eliminate the exponential term, and then that makes solving r a lot easier. We just divide across by 0.5, or equivalent to multiplying by 2. Likewise down here, it's for a 1 year term. We don't know the rate of interest, that's what we want to find. There's no coupon, you pay 89 today, and in 12 months time you get 100 back. So to solve for r, divide both sides by 89, 1.12. To eliminate e, we take the natural logarithm both sides, and this side we're left with r. On this side we take the natural logarithm of 1.123596, and that yields us 11,653. So that's equivalent to saying the 6 month zero rate, zero coupon rate, is 12.375, and the 12 month zero coupon rate is 11.65, and that's what we're trying to find out. That's what these term structures are actually about. We're trying to determine the zero. Once we're estimating the yield curve, we're trying to take the zero coupon rate. The juice, what the interest rate is, consistent by stripping out the coupon. Okay, so we go back in, and of course we have the other two bond instruments that we need to look at. You invest $94.84, get 4 coupon every 6 months for 18 months, get $100 back at the end of 18 months. Okay, so that's equivalent to a bond structure like this: 4 at month 6, 4 month 12, 104 at month 18. You pay $94.84 for that. We know what the 6 month and 12 month interest rate is because that's what we just worked out here and here. And the idea that we take these earlier rates and recycle back in here and here is equivalent to this idea of bootstrapping, right? So the technique we're using here is a bootstrap, and as in all bootstrapping, if you strap your boots up, you start at the bottom and work the way through, and you can't strap your boots by starting at the top and going down 2 and back 3 and so on, right? It becomes a mess. So the idea of bootstrapping here when getting the yield curve means we determine the earlier yields, zero coupon yields, and then use those. So we take these rates and we use them here. And that implies then that the only discount factor that's unknown here is this R. Okay, so the only discount factor that's unknown here is this R. And again, we can solve. We can take these out, discount them, get a value of 732. Then strip that away from the bond price. So we're stripping out the coupon, the present value of the coupons. And we're left with this 104E negative 1.5 R. And that's set equal to this 8752. And then to solve for R, same exercise as before, divide both sides by the 104. And then to get rid of the exponential, we take the natural logarithm both sides. And because we have 1.5 this side, we have to divide over. Then when we estimate that, we have 11.5. So the 18-month zero coupon rate is 11.5%. And then finally, to get when we take that rate again and we recycle, we look at the final bond then, face value 100, market price 97.12, semi-coupon of 5 every 6 months for 2 years. Let's look at the structure of that bond. That's the structure that we have here. And what we discover is the rates we estimated earlier, including the 11.5 that we have here, will be recycled or bootstrapped back in. And so the bond structure of 5, coupon of 5 in month 6, in month 12, of 5 in month 18, and then the face of 100 plus the 5 coupon at month 24 or year 2. That sequence of payments is going to be made in the bond. The bond is currently selling for 97.12. We have to solve only one unknown here in this, it's R. We can take these bonds, coupon payments in the bonds, discount them at their respective rate of interest, get the present value of the coupons, bring over, so the economic interpretation of subtracting away is we're stripping off the effects of the coupons, of the earlier coupons, and then we're just left with an amount of money that gets invested, equivalent to the coupons being stripped out, and then the return of 105 at the end of 2 years. So it's a straight up put some money in today and a return then in 2 years' time. Again, we divide both sides by 105, and then to get rid of e, the exponential, we take the natural logarithm both sides. The natural logarithm of e to the power of negative 2r is negative 2r. So that's a handy way of getting rid of the natural logarithm. But again, we repeat that exercise, and when we run that, we find that the estimated value for the 2-year, the zero coupon yield at the 2-year period, at the 2-year term, is 11.299.